Imagine standing on a quiet hill, watching the sky burst into a symphony of colours as the sun peaks above the horizon. It's a daily spectacle that many of us take for granted, the warm hues of orange, red and pink splashing across the sky. Yet, this beautiful sunrise is only the final chapter in the light's long journey. If we trace the path of these photons from their endpoint in the retina at the back of your eye, through the Earth's atmosphere, across the 150 million kilometer void separating our planet from its host star, and finally through the varied and tumultuous layers of that star, we discover the source of the warmth on your face and the colors painted across the sky. The sun's core, a nuclear engine that has been raging for 4.5 billion years. Born in a cosmic nursery from the remnants of ancient stars, the glowing sphere of searing plasma that dominates our sky is the product of complex forces that have played out over millennia. But how much do we really know about such a pivotal part of our lives? What are the processes that govern its colossal power? What are its most awe-inspiring features? And how are scientists piercing its depths to uncover its mysteries? I'm Alex McColgan, and you're watching Astrum. Join me in this supercut as we dive into the depths of our sun and learn what secrets lie behind the blinding curtain of light and time. To understand how the sun formed, we must go back to before our solar system even existed, about 4.6 billion years ago. At that time, in a relatively quiet region of the Milky Way galaxy, a massive cloud of gas and dust, known as a giant molecular cloud, drifted silently through space. This was no ordinary cloud. It was immense, possibly spanning hundreds of light years across, with a mass equivalent to millions of suns. Within this cloud lay the scattered remnants of ancient stars that had long since exhausted their nuclear fuel and exploded as supernovae, casting their enriched contents into the cosmos. This stellar debris included a mix of elements such as hydrogen and helium, the building blocks of stars, along with heavier elements like carbon, oxygen, nitrogen, and iron. The presence of these elements made this molecular cloud fertile ground for forming new stars and planetary systems. However, such a massive cloud requires a trigger to initiate the cascading collapse that results in stellar birth. Scientists believe that this trigger could have been a shockwave from a nearby supernova explosion that compressed parts of the cloud, causing it to fragment and collapse into regions of higher density. This collapse marked the beginning of the pre-solar nebula, the dense region within the molecular cloud that would eventually give birth to our solar system. Some scientists have even proposed a name for this hypothetical exploding star, Coatlicue. Named after the Aztec goddess of earth and fertility, Coatlicue symbolizes the death and rebirth cycle, where in this case, the death of one star can seed the formation of new ones. As the gravitational collapse of the giant molecular cloud progressed, it did not result in a single massive object, but rather fragmented into multiple dense clumps. This fragmentation occurs due to a phenomenon known as Jeans instability, named after the British physicist Sir James Jeans. The Jeans length is a critical distance within a cloud at which the forces of gravity are balanced with the natural internal gas pressure that keeps the cloud propped up. When a defined section of the cloud exceeds the Jeans length, it will collapse in on itself. Different regions within the molecular cloud exceed this Jeans length at different times due to variations in density and temperature. As these regions become gravitationally unstable, they collapse independently to form multiple protostellar cores, as opposed to one single massive body. The protostellar core was the earliest phase in our sun's life that was recognizably star-like, crunching itself into a tighter and tighter sphere by the ever-clenching fist of its own gravity. The core is surrounded by infalling gas and dust. As more material accumulates, the core becomes denser and hotter, setting the stage for the next phase of star formation, the protostar. Once a protostellar core becomes sufficiently dense and hot, it evolves into a protostar. The central region has heated up to the point that it begins to emit light and heat from the energy released by gravitational contraction. But its core has yet to reach the temperatures required to ignite nuclear fusion in the core. As the protostar continues to accumulate material and grow in mass, the pressure and temperature in its core increase dramatically. Our Sun developed through this embryonic state of contraction and heating for millions of years, before eventually building up its core temperature to about 10 million degrees Celsius, at which point hydrogen nuclei began to fuse into helium. And with that, the Sun was born. At this stage, the innate angular momentum of the surrounding material that shrouds the infant star generates rotation. A cloud of this size will always have some slight rotation, nothing in the universe is still, and conservation of angular momentum dictates that the cloud must spin faster and faster as it crunches down into tighter space, similar to how a spinning figure skater speeds up as they tuck in their arms. Around the equator of rotation, some of the material is moving fast enough to stay in orbit, but higher up and lower down, the momentum is insufficient to resist the protostar's ravenous pull and falls helplessly into its jaws. And so, the cloud flattens out into a disk, a protoplanetary disk. This disk is a cosmic lottery. As it cools and coalesces, planets, moons, asteroids, and comets will be relentlessly created and destroyed. Some material will be robbed of its momentum and tumble into the Sun, while neighbouring matter will go on to become part of the many bodies that make up our solar system today. With its new ability to fuse hydrogen atoms into helium, the Sun could finally generate energy to push back against the forces of gravity that sought to squeeze it further. The energy streaming out of the fusion reactions created an outward radiation pressure that balanced the inward gravitational pull of the gas, allowing the young star to achieve a stable state known as hydrostatic equilibrium. In this state, the star no longer contracts under its own gravity, and it enters a stable phase of its life known as the main sequence. This balancing act between internal pressure pushing outward and gravity crushing in is the axis that defines every stage of the Sun and all stars' lives. We saw it during the initial collapse, and here as it settles into a stable main sequence star, and it will be the pendulum that eventually swings towards its dramatic death. For now, let's unpick the process of nuclear fusion and how it's capable of keeping an object as massive as the Sun stable and steady for billions of years. To understand how nuclear fusion occurs in the Sun, we need to examine extreme conditions present within its core. Today, temperatures reach around 15 million degrees Celsius and pressures more than 250 billion times that of the Earth's atmosphere. In this blazing cauldron, hydrogen atoms are stripped of their electrons, forming a plasma composed of free protons and electrons. Under such intense conditions, these protons, normally repelled by their shared positive electric charges, are forced into extremely close proximity. The force that usually keeps them apart is the Coulomb force, an electrostatic repulsion between positively charged particles. It's exactly the same force that resists as you try to push the same ends of a bar magnet together. Overcoming this force is the primary challenge for nuclear fusion to occur. Despite the extreme kinetic energy of protons in the Sun's core, most collisions are still not energetic enough to overcome the Coulomb barrier. Under normal conditions, protons need immense energy to get close enough for the strong nuclear force to bind them together. This barrier is so significant that physicists around the early 1920s, using a classical understanding of how particles interact with each other, determined that fusion should not occur at the temperatures and pressures found in the Sun's core. To solve the puzzle, we needed a scientific model that has come to explain many of the seemingly impossible phenomena we observe in the universe: quantum mechanics. The quantum mechanics revolution of the 1920s introduced the concept of particles behaving both as particles and as waves. One of these phenomena is quantum tunneling, where particles have a certain probability of tunneling through a barrier even when they lack the classical energy needed to overcome it. In the Sun's core, quantum tunneling allows a small fraction of protons to effectively bypass the Coulomb barrier without having to climb over it in the classical sense. Even though these protons do not have enough kinetic energy to overcome the electrostatic repulsion directly, quantum mechanics gives them a chance to appear on the other side of the barrier. To visualize this process, consider a diagram of the Coulomb barrier. In the diagram, you will see a high energy barrier representing the repulsive electrostatic force between two protons at varying distances. The energy needed to climb over this barrier is represented as a peak. The calculations of a classical physicist would require the Sun to have temperatures high in the billions of degrees Celsius, thousands and thousands of times higher than the Sun's core, to hurdle this barrier. But quantum mechanics allows for the probability wave of a proton to tunnel through this barrier, appearing on the other side without ever going over the peak. This tunneling effect is what enables fusion to occur in stars like the Sun, despite the seemingly insurmountable Coulomb barrier. Once a proton has tunneled through the Coulomb barrier, it gets close enough to another proton for the strong nuclear force to take over. The strong nuclear force, which is far more powerful than the Coulomb force, operates only at very short ranges, on the order of femtometers, where 1 femtometer is equal to 10 to the power minus 15 meters, roughly the size of a single proton. The strong nuclear force binds the protons together, but this is only the first step in a series of nuclear events known as the proton-proton chain. The proton-proton chain reaction is the dominant fusion pathway in the Sun and other stars of similar size, accounting for roughly 99% of the Sun's energy production. It starts with two free-roaming protons combining to form deuterium, a heavy isotope of hydrogen, along with the emission of a positron and a neutrino. This step is rare but essential, as it allows the fusion process to continue. The deuterium then rapidly fuses with another proton to form helium-3, releasing a high-energy photon, a gamma ray. In the final step, two helium-3 nuclei collide and fuse to form helium-4, releasing two protons and a significant amount of energy in the form of radiation. While the proton-proton chain is the dominant fusion process in the Sun, there is another pathway at play, particularly in stars hotter and more massive than our Sun. This pathway is known as the CNO cycle, short for carbon, nitrogen, oxygen. In this cycle, carbon, nitrogen and oxygen nuclei act as catalysts to fuse protons into helium. The CNO cycle is more efficient at higher temperatures and only contributes a small percentage of our Sun's energy output. The energy produced in these fusion reactions comes from a small amount of mass being converted into energy, as described by Einstein's famous equation E equals mc squared. In the fusion process, the mass of the resulting helium-4 nucleus is slightly less than the combined mass of the original 4 protons. This missing mass is not lost, but rather converted into energy that radiates outward from the Sun. Every second, the Sun converts about 4.3 million tons of its mass into energy. That's right, the Sun is losing mass all the time. To put this into perspective, this is the equivalent of the mass of about 3 million cars being turned into pure energy every second. This is the energy that ultimately powers the Sun and provides the light and heat that reaches Earth. But before these photons pouring out of these reactions can reach the Earth and everything else in the solar system and beyond, they must first escape the 700,000 kilometers of chaotic solar interior that lies above them. To truly grasp the complexity of the Sun and its stratified layers, let's follow a single photon, a particle of light, from its creation within a proton-proton reaction all the way to the surface. This journey is anything but straightforward. In fact, it will take thousands, if not hundreds of thousands of years for this photon to complete its journey, passing through several distinct layers of the Sun, each with their own unique properties and behaviors. As we've already found out, our photon's journey starts in the core, a region that spans about 25% of the Sun's radius, but holds nearly half of its total mass. And, as we've also heard, the core is incredibly dense. At around 160 grams per cubic centimeter, it's over 20 times denser than iron. To put that into perspective, if your phone was made of material that dense, it would weigh as much as a heavy-duty sledgehammer. For our photon, this means that the environment is so tightly packed with particles, it cannot travel far before being absorbed by a neighboring particle. Of course, not long later, that particle will pack the photon's bags and send it out into the melee of the core for another particle to catch and release in some other random direction. It's a bit like trying to navigate through a dense crowd, where every few steps you bump into someone and have to change direction. This constant interaction of absorption and re-emission is what gives the core its chaotic nature, resulting in a journey for a photon that is more of a random walk than a direct path outward. This random movement of photons is reminiscent of Brownian motion, where particles suspended in a fluid move erratically due to collisions with smaller, fast-moving molecules. And there is no preference for the direction that a photon could fly back out of a particle that had just absorbed it. In theory, a photon could make it all the way to the surface of the Sun before random chance directs it back towards the core. To add to the complexity, as photons are continuously absorbed and re-emitted, the energy gradually decreases from gamma rays to X-rays and eventually to visible light as they move towards the Sun's outer layers. Understanding the processes occurring within the Sun's core has been a challenging endeavour for astronomers. The core is completely obscured by the outer layers of the Sun, meaning we cannot directly observe it through any form of light. Instead, scientists have developed ingenious methods to infer the dynamics of the roaring inferno below. One of the key techniques is the study of helioseismology, the observation of waves rippling across the Sun's surface. Just like seismologists study earthquakes to understand Earth's interior, helioseismologists measure the vibrations of the Sun's surface caused by sound waves that travel through its interior. These sound waves are influenced by the temperature, density, and composition of the Sun's layers, allowing scientists to construct models of what is happening deep within. Solar neutrinos, elusive subatomic particles that I've talked about in a previous video, are also released during the fusion reactions in the Sun's core. Neutrinos interact so weakly with matter that they can travel straight out of the Sun in just 2 seconds, hardly aware of the tangle their photon counterparts are caught up in. For decades, solar neutrino detectors on Earth measured fewer neutrinos than predicted by theoretical models, leading to what was known as the solar neutrino problem. It wasn't until scientists discovered that neutrinos change their properties, or flavors, on their journey to Earth that the mystery was resolved, confirming both our understanding of particle physics and the nuclear processes in the Sun's core. Next, the photon enters the radiative zone, which extends from the edge of the core to about 70% of the Sun's radius. Here, temperatures gradually drop from 15 million degrees to around 2 million degrees Celsius. The density of matter also drops, going from around the density of gold in the zone's depths to less than water near the top. The dominant energy transportation method is still this frenetic process of photons skittering through the layer, carrying their energy on average towards the surface. And as the density of the plasma continues to decrease as we move outward, our photon has slightly more wiggle room, capable of bigger leaps between interactions. But even here, outside of the core, the sun's material is still so opaque that even a few centimeters could block out as much light as hundreds of meters of water. We are able to envision such precise models of the sun's interior because of models like the Standard Solar Model, or SSM. It is a mathematical framework based on the principles of hydrostatic equilibrium, energy conservation, and radiative transfer. Essentially using our understanding of how materials and fluids behave here in our laboratories on Earth to infer the properties of a place out of our reach. The SSM models how energy is passed between particles in its complex equations, describing how photons are transported through the dense plasma. This allows us to calculate how transparent the solar material is to radiation at different temperatures and densities, and from there we can work out where the radiative zone ends and the next layer begins. This is one of my favorite things about mathematics. It allows us to explore environments that we can never visit, almost like how quantum tunneling allows protons to jump over the Coulomb barrier and produce the photons we are now following. As our photon approaches the upper boundary of the radiative zone, it enters the tachocline, a thin, transitional layer where the radiative zone meets the next layer, the convective zone. The tachocline is an environment of extreme contrast, where the relative uniformity of the radiative zone meets the boiling, bubbling convective zone. The strange conditions in this extremely thin layer likely plays a key role in the solar dynamo that generates the sun's magnetic field. The tachocline is thought to twist and amplify the magnetic field, shaping the sunspots and solar flares that define the star's surface. Zipping through the thin tachocline, our photon arrives at the convective zone. Stretching out from about 70% of the sun's radius to just beneath the visible surface, the photosphere, the temperatures have dropped to below 2 million degrees Celsius. Now, the sun's plasma is no longer dense enough to effectively transfer energy by radiation. Instead, the plasma becomes unstable and begins to move in massive convection currents, much like boiling water in a pot. Hot plasma rises towards the surface in large cells called granules. These granules, with diameters of thousands of kilometers, surge upward under their power of buoyancy at speeds of hundreds of meters per second, like a beach ball that you force below the water, rushing to the surface as it squirms from under you. The force required to move this volume of matter against the sun's gravity is astonishing. Imagine the force of 10 billion hurricanes, and you'd be just starting to get close to the energy necessary. This convective process moves energy much more efficiently than the radiative zone, creating turbulent, rolling waves of plasma that churn vigorously. This is a significant change in how energy is transported. While photons still interact with particles, the primary mechanism of energy transfer in the convective zone is no longer the random absorption and re-emission between particles, known as radiative diffusion, but rather the movement of hot plasma rising and cooler plasma sinking. This convection motion carries the energy outward more efficiently than in the radiative zone. Upon reaching the top of the convective zone, the photon is carried to the photosphere, the sun's visible surface. Temperatures have now cooled to about 5,500 degrees Celsius, and the plasma has thinned enough for photons to escape without being constantly reabsorbed. It is from this thin, roughly 500 kilometer deep layer that the light we see from the sun is emitted. Above them lies only the sun's corona, which is itself a fascinating environment, but only around a billionth of the density of the photosphere, and therefore not much of an obstacle to our photon. It is incredible that an object like the sun, that many refer to as a ball of gas, can have such a sharp boundary. But the photosphere is where our photon finally breaks free, traveling at the speed of light and beginning its journey across the vastness of space. Our neutrino friend that was created at the same time? It's long out of the Milky Way by now. Since settling into its stable main sequence phase, nuclear fusion has altered the strength of the Sun's layers, gradually increasing its brightness over billions of years. This is because the fusion process inevitably leads to changes in the composition, density, and temperature of the Sun's core, which in turn affects the overall behavior and the future of our star. As hydrogen fuses into helium, hydrogen gradually depletes in the core, and helium ash begins to build up. Unlike hydrogen, which readily undergoes fusion at the Sun's current core temperatures, helium requires much higher temperatures to fuse. As the abundance of helium increases, the core becomes denser. Helium nuclei are more massive than hydrogen nuclei, and as more helium collects in the core, the overall density increases. At the same time, because helium is not fusing and creating energy, it does not contribute to the outward radiation pressure that counterbalances the Sun's immense gravitational pull. The result is that gravity will begin to dominate, causing the core to contract further. To prevent collapse under its own gravity, the Sun must increase its core temperature as helium builds up. The hotter core turns up the dial on hydrogen fusion because nuclear fusion rates are extremely sensitive to changes in temperature. This increase in fusion releases more energy, which results in a brighter star and temporarily restores the balance between gravity and radiation pressure. Through this process, the Sun's energy output has increased by about 30% over its lifetime, and this trend will continue for billions of years as long as hydrogen fusion dominates in the core. In the radiative zone, the layers have grown hotter and more opaque. The rising temperature of the core means more energetic photons are produced, which are more prone to interacting with the surrounding plasma and pinballing around. As a result, this zone has become less efficient at radiating energy outward, trapping photons for longer before they can continue their escape. The convective zone has also expanded slightly over time due to the increased energy production. As the Sun continues to burn through its hydrogen fuel over the next 5 billion years, its core will eventually be left overburdened with inert helium that can no longer sustain fusion under its own pressure. When this happens, the Sun will evolve into a red giant, dramatically expanding and engulfing its inner planets, including Mercury and Venus and possibly the Earth. In this phase, the core will contract and heat up until it ignites in a helium flash, starting the fusion of helium into heavier elements like carbon and oxygen, yet again swinging the pendulum between the relentless gravitational hammering and the resisting forces of energy from the core. This process will create new layers and cause the Sun to swell even further before shedding its outer layers to form a ghostly remnant, a planetary nebula. The core that remains will cool and fade, becoming a white dwarf, a dense, Earth-sized ember of a once raging fire. With that, we already have an overview of the past, present, and future of our Sun. But there are sides to the Sun we have not yet explored, and many mysteries still lie within its blazing light. But sometimes the secret to understanding something is in learning to see it differently. Visible light is not the only wavelength of light out there, and thanks to the advancement of modern technology, we are now able to see the Sun using infrared light, X-rays, and other spectra. And in doing so, we reveal some of the Sun's fiercest beauty and its most awe-inspiring features. This video doesn't have a sponsor, but it's still made possible thanks to all of you who support the channel on Patreon. To say thank you, we've been uploading these breathtaking images of space as screensavers for your phone and computer. There's the Milky Way, Venus, and now for today's video, the Sun. You can get the screensavers when you join on Patreon, or you can buy a physical print from our Displate store. Not only do you get these beautiful posters, but you'll also be supporting our channel. Links are down below, and a big thank you from the entire Astrum team. Where to begin? We just followed a photon from the center of the sun to its outer extremities. But now, let's do the reverse. Like eating a fruit by starting with the outer layers and working your way in, let's start our investigation with the outermost layer of the sun's atmosphere, the corona. The following image was taken by the Solar Dynamics Observatory, or SDO, a NASA space mission launched back in February 2010. SDO aimed to better understand the solar variations that influence life on Earth and our technological systems by studying the dynamic solar surface and atmosphere at different electromagnetic wavelengths. By looking at light beyond the visible range, NASA was able to pick out normally invisible details crucial to our understanding of the sun. This image was taken using a 19.3 nanometer wavelength, representing light found in the extreme ultraviolet region. At a wavelength corresponding to a color temperature of 1 million Kelvin, we can clearly see the higher region of the sun's corona. Interestingly, the sun's corona can also be seen by the naked eye on rare occasions, such as during a total solar eclipse. When the moon is perfectly aligned between the Earth and the sun for a fleeting period of time, the view of the central, brighter disk, known as the photosphere, is fully blocked, revealing a radiant exterior. While this is a breathtaking view already, the corona is still nowhere near as detailed as it is in this image taken by the SDO. This makes it a useful tool for scientists' studies. But let's go a little deeper, to features of the sun just beneath the corona. At a color temperature of 20 million Kelvin, the intensely vivid spots indicate events known as solar flares. Here is some footage of a particularly busy week for flares back in August 2022. I've always found solar flares to be both terrifying and hypnotizing. They are colossal explosions where the sun spews out an immense amount of electromagnetic radiation. They are caused when magnetic fields cross, distort, and reorganize themselves rapidly. This activity is created by the turbulent nature of the plasma within the sun itself, from which the fields ultimately originate. Solar flares and coronal mass ejections both are highly energetic events, on the scale of millions of nuclear weapons in a single instant. The magnetic reconnection events that cause them can send vast amounts of radiation, in the case of solar flares, and matter into and away from the sun. In the case of coronal mass ejections, millions of tons of charged material flies out from the sun at hundreds or even thousands of kilometers per second. But they are not the only feature of the sun's atmosphere venting radiation. Coronal holes, indicated here by this darker region on the sun, are another fascinating feature which we'll take a closer look at using extreme ultraviolet light. Coronal holes are areas of cooler, less dense plasma which are magnetically open, meaning that rather than forming closed loops that go back to the sun's surface, the field lines travel outward across the solar system. These areas allow solar wind particles to escape more easily into space. When these solar winds are directed towards and collide with Earth's magnetosphere, beautiful auroral lights dance across the night sky at the Earth's polar regions. Using ultraviolet light gives us a much better view of these fascinating features of the sun's outer layers. Non-visible spectrum light is an incredible tool, and there are so many different features in the sun's outer layers to look at. There are solar filaments, known as solar prominences, the large loops of plasma that rise from the sun's surface. These enormous loops are large enough to make the Earth look like a tiny speck and can stretch hundreds of thousands of kilometers into space. They can form in as little time as a day, but a stable prominence can remain in the corona for several months. In this example, we watch as a solar prominence snakes its way out of the photosphere and into the sun's atmosphere. Although this video is sped up so the minutes seem like seconds, when you consider the size of the prominence, it becomes clear how swiftly the sun's intense magnetic fields are causing this material to move. One fact you might not know about the sun's atmosphere is that it sometimes rains there. Not all of the charged plasma fired into the sun's corona continues out across the solar system. Some remains in the corona, getting trapped and cooled until it falls back to the sun's surface as a shining rain. This coronal rain is beautiful to look at, but is best observed from a distance. It's still millions of degrees in temperature. Of course, falling gently back to the sun's surface is only the fate of some of the sun's plasma. This is where the comparison to Earth fails. After all, on Earth, the clouds do not crack like a released elastic band firing into space. On the sun, thanks to tightly wound magnetic fields, they do. This is a time-lapse of a coronal mass ejection. Watch as the structure forms at the bottom left of the sun for some time, before eventually snapping and sending billions of tons of plasma out across the solar system. Even with the Earth's magnetic field, being hit by a powerful one of these could be devastating for our satellites and electrical grids. All these structures are imaged by the SDO here utilizing a 30 nanometer wavelength of light, which corresponds to the extreme ultraviolet portion of the electromagnetic spectrum. Timing is important when trying to image these features, as they are more common in certain years than in others. In fact, each structure is dependent on the solar activity of the sun, alternating around an 11-year solar cycle. We'll talk more about that later. But there's more to learn. Just as using visible and ultraviolet light shows us different things when looking at the same feature, using two different wavelengths of non-visible light can also be eye-opening. To demonstrate this, take a look at these two images of the sun's corona. Taken over the same time period, the following two images use different wavelengths of light. The first, imaged at a color temperature of 600,000 Kelvin, depicts the quiet corona and features coronal loops. The second, imaged at a color temperature of 2 million Kelvin, displays the much hotter active regions of the corona. The stark comparison between the two images highlights the importance of using different approaches when investigating the star. What may initially appear to be a singular solar phenomenon can be revealed as a complex, intertwined chain of events, and we still haven't technically made it through the sun's atmosphere yet. Moving further inwards, let's look at another image produced by the SDO utilizing a 160 nanometer wavelength of light, this time of the transition region. The transition region is a layer which sits between the sun's corona and the chromosphere, the lowest layer of the sun's atmosphere. It's a very shallow layer, approximately 100 kilometers in thickness. In this region, the thermal temperature of the sun rises dramatically from around 8,000 to 500,000 Kelvin. For an earthly comparison, fiercely scalding lava erupting in Hawaii is 1,170 degrees Celsius or 1,443 Kelvin. The temperature at the lower, deeper end of the transition region is almost 6 times hotter than this. At the upper end of the transition region, the temperature is more than 346 times hotter. Traveling even deeper, we find ourselves immersed in the sun's chromosphere, which is the last layer of atmosphere before we reach the sun's surface itself. Imaged here, using 170 nanometer ultraviolet light, it is estimated to be approximately 1,700 kilometers thick. Closely inspecting the chromosphere, we identify some mesmerizing features known as spicules. Swaying like long, wavy grass blowing in the wind, these long jets of plasma shoot upwards from the sun's surface at speeds up to 100 kilometers per second, approximately 282 times faster than the speed of sound, and can reach lengths of nearly 10 kilometers, over 1 kilometer taller than Mount Everest. Forming and vanishing in around 5 to 10 minutes on average, the processes behind these spicules were widely unknown and debated for some time, as it wasn't clear how magnetically charged particles could ever escape the sun's magnetic fields at that level. That is, until 2017, when a team of scientists working on an extremely detailed model of the spicules discovered that their origins must be related to neutral particles. Scientists had not originally included neutral particles in their models of the sun, as they didn't think they affected the motion of the magnetically charged particles. But once they were added, it transpired that the neutral particles gave the magnetically charged particles unexpected buoyancy they needed to escape the sun's plasma and shoot up into spicules. Descending further through the sun's lower atmosphere, we eventually reach the photosphere, the surface of the sun itself, which is best imaged using visible light. While the edge of the photosphere appears sharp and precise, as it often does to our naked eye, this is simply due to how far away the sun is. The sun itself is not solid at all. Since it is too hot for matter to exist in a solid, liquid, or gas state in any region of the sun, it can only be plasma, referred to as the fourth state of matter, and is estimated to make up 99.9% of all the matter in the universe. Plasmas tend to behave a lot like gases, except they are made up of a mixture of ionized atoms and free electrons. The photosphere is the outermost layer in this image, around 400 kilometers thick. It is not a fixed, solid boundary of the sun, unlike what this image may suggest. And sadly, it is the deepest layer of the star which scientists can measure directly. At a closer look, you may notice some dark spots on the left-hand side. These are known as sunspots and appear darker than other parts of the photosphere due to their cooler temperatures. But that's only in comparison to their scorching hot surroundings. Unlike coronal holes, sunspots form in areas where magnetic fields are particularly powerful. Here, heat becomes trapped beneath the photosphere due to decreased convection within these areas. When comparing this image of the sun to a previous one taken using extreme ultraviolet light over the same period, a connection between sunspots and solar flares emerges. The captivating solar flares and sunspots coincide at the same location. From peering beneath the surface, it becomes clear that one must lead to the other. Sunspots can be anywhere between 15 kilometers in size to 160,000 kilometers, multiple times the size of the Earth. Now let's take a closer look at some similar sunspots. This image was taken using the Swedish Solar Telescope, based here on Earth, and using a wavelength of visible light of approximately 400 nanometers. Next to and surrounding the sunspots, the photosphere is saturated with these jagged-edged, endlessly shape-shifting cells, which doesn't look dissimilar to lava as it cools and cracks. However, these cells are around 1,000 kilometers wide and are known as solar granules. Consider them from the top layer of a churning convection cell underneath. Brighter areas inside each granule represent fluid of unimaginable temperatures rising from within the sun's upper interior layer to its surface. Upon reaching this boundary, the fluid has nowhere to go except to spread outwards and across. After cooling gradually, the fluid sinks back inwards via the rough, dark boundaries surrounding each cell before repeating the cycle. This process closely resembles the convection currents within the Earth's mantle, responsible for driving plate tectonics. This process is no joke. While on average it is estimated that each granule lasts for as little as 20 minutes, the flow within the cells reaches supersonic speeds of more than 7 kilometers per second, generating waves on the sun's surface due to sonic booms, but we'll get to how loud the sun is later. Fascinatingly, these granules can also be seen in the full disk view we saw earlier, utilizing the same wavelength of visible light. You may think this image looks quite grainy for such a high-tech space probe, and you're right, it does. But that graininess is the granules on the photosphere of the sun, not a processing effect or excess noise in the image. Sadly, our journey ends here, as scientists have not yet figured out how to image deeper into the sun, using either visible or non-visible light. Much of what lies beyond this layer remains shrouded in mystery, but we can see the benefits of using light of all different spectrums in our study of the sun. The sun is abuzz with lively activity, and so much of it would be invisible to us were it not for these imaging techniques. Much of what goes on within the sun is undetectable to us, but its influence on our lives is no less subtle. And yet, its touch on our lives is pervasive, shockingly so. If I were to tell you that the cycles of the sun could affect your entire life, you might think that I was suddenly taking a turn away from astronomy and into astrology. While there are many people in the world who believe that you can learn things about your future by studying the position of stars and planets, it's not a position I tend to take on this channel. I'm more interested in the beauty of space and the mechanisms that explain why it is the way it is. But sometimes there is a grain of truth behind even the most surprising of stories. So allow me to put on my prophesying hat. While I'm no writer of horoscopes, I will predict that based on the current state of the sun, this year in 2025, you might be more likely to experience bad health, less reliable technology, see warmer weather with fewer clouds, and possibly could be influenced in other surprising ways. How do I know? Because it turns out the sun, that giant ball of fire in our sky, is not just the place we get our energy from. Science is starting to show that its 11-year cycles might just be the metronome measuring out how life on our planet tick, tick, ticks. How is that possible? Allow me to explain. It's no surprise that the sun is influential to life on Earth. After all, in many respects, it is life's origin. Life on Earth needs energy to function, and the sun frequently provides that energy. Light for plants, plants for herbivores, herbivores for carnivores, all the way up the food chain. It's hard to find anything on Earth that could live without our sun. But beyond the gift of that life-sustaining energy, it's easy to think of the sun as fairly static. We see it rise and fall in the sky, but we rarely notice it undergoing any sort of change. This, however, is an illusion. The sun changes all the time. We've already covered much of this. The sun is a boiling, shifting sea of barely restrained plasma, which frequently isn't restrained. The sun operates on an 11-year cycle that alternates between a period of low activity, the solar minimum, to a much higher level, the solar maximum, and then back again. Sunspots, solar flares, and CMEs all become more common during the solar maximum. You are 50 times more likely to see a solar flare during solar maximum compared to the sun's minimum, and large CMEs go from happening once every few days to multiple times in a single day. This is known as the Schwabe cycle. Interestingly, this represents one half of a larger cycle known as the Hale cycle, which maps the changes in the sun's magnetic polarity. Once every Schwabe cycle, every 11 years, the sun's magnetic north pole and south poles swap places. When another Schwabe cycle occurs, the poles swap back. Tick, tick, tick. This constant rising and falling of solar energy levels thrums through our planetary system, rising and falling like a heartbeat. And surprisingly, even though we can't see it, we here on Earth move to its rhythm. We don't really understand why the sun goes through this cycle. It's clearly related to the magnetic processes that exist within the sun itself. Yet, although we have observed these cycles in action for the last 200 years and have seen evidence of their influence on the Earth over the last 10,000, we're still no closer to figuring out why the sun cycle has a length of that particular time period rather than any other. What force drives it? Lacking any other obvious answer, some scientists have tried to connect the orbital length of Jupiter, also about 11 years, to this cycle length, but this could easily be a coincidence. Although Jupiter represents 2.5 times the combined mass of all the other planets in the solar system, and definitely exerts some gravitational pull on the Sun, its orbit cannot explain the variations, seemingly random, that the Sun's cycle undergoes. Much of what goes on within the Sun is a mystery to us, but its influence on Earth, that is much easier to see. It begins with the space around us. Space is more and more important to modern civilization, so it shouldn't be surprising that CMEs and solar storms streaming out from the Sun more regularly would have an impact on the technology we have up there. Scientists are able to predict the arrival of a solar storm, known as a geomagnetic storm, by the time it arrives at Earth, days or even weeks in advance. This allows astronauts to go into safe shelters to hide themselves from harmful rises in radiation levels, and it also allows the delicate hardware on satellites to be powered down to prevent that hardware from being fried. This is important, as solar radiation can cause unexpected electrical currents to form in wiring, overloading systems that haven't gone into a safe standby mode. But there's another aspect to geomagnetic storms that you might not expect. All of that radiation has an impact on the atmosphere itself. It warms it, albeit just a little. As the atmosphere warms, it expands, and this has an impact on our satellites. In space, there is no drag, so objects can orbit practically forever. Well, this isn't entirely true, and satellites in low Earth orbit do occasionally, about 4 times a year, need to expend fuel to correct their orbits, as there is still a tiny amount of atmosphere up there. But when a geomagnetic storm occurs, the atmosphere blossoms upwards, and low Earth orbit satellites have to maneuver every 2 to 3 weeks to keep from falling from the sudden friction. And this isn't always enough. In 1989, there was a geomagnetic storm that was so powerful it knocked the NASA Solar Maximum mission out of the sky, as an increase in atmosphere suddenly slowed the satellite down. Ironically, the mission had been studying solar flares. This is not an isolated incident. NORAD, the Northern American Aerospace Defense Command, has to relocate hundreds of satellites after each geomagnetic storm, as they have been knocked out of their old orbits. Radiation can also influence our ionosphere, filling it with charged plasma. This can have a slight lensing effect on your GPS systems, reducing their accuracy from within a meter to over 10 meters. The next time you look on Google Maps and it thinks you might be a street across from where you are, a geomagnetic storm might be to blame. Our power grids brace themselves every 11 years for the uptick in these current-inducing events to keep themselves from being overloaded. Amateur radio enthusiasts and airline pilots actually enjoy this phenomenon. They take advantage of these strengthened atmospheric conditions by bouncing signals off them like stones skipping across a lake, significantly increasing their distance on high-frequency radio frequencies. Still, for everyone who isn't into ham radio, as I predicted in my horoscope, this all adds up to some less reliable technology. The fact that the next solar maximum is already underway makes me quite confident in my prophesying. There are some bright sides to this. As space weather becomes more turbulent, parts of the world such as Canada see a rise in the number of auroras dancing hypnotically across the sky. Aurora chasers report rises in sightings from a few times a year to as many as twice a month during the most energetic parts of the Sun's 11-year cycle. So much for the Sun's influence on space and our technology. You might think that that's the end of it. The Sun cycle might influence machinery, but it's not going to make much difference on anything alive, right? If you think that, you'd be wrong. It's not for nothing that the rest of my horoscope mentioned poorer health. There's growing evidence that the Sun cycles can even influence ecosystems and species themselves, including humans. Some of this is incidental. When the Schwabe cycle is at the solar minimum, the Sun exerts less pressure through its solar winds, which means, ironically, that we get less protection from our heliosphere from cosmic radiation. This form of radiation is highly energetic, but fortunately rarely makes it through our atmosphere for that very reason, as it's likely to be absorbed or deflected by a passing air molecule. But reaching the atmosphere is all that's needed to produce an effect. There is a theory, although still far from certain, that this extra radiation could be creating nucleation sites in the atmosphere that seed extra clouds, influencing our weather. Even if that's not occurring, during solar maximum, the space weather hitting our atmosphere can raise global temperature slightly. As my horoscope predicted, a warming of the weather. Not by much, it should be said, less than half a degree, and the temperature always eventually returns to where it started, but it's enough that it's noticeable to species paying attention to temperature, for instance to decide when to start the mating season. Studies of birds have shown that on warmer years they tend to lay eggs earlier. Curiously, a study published in 2009 by researchers in the Netherlands went as far as to show that the laying times of blue tits were also affected by the number of sunspots occurring, which even the researchers found hard to explain. It's not like birds can look at the sun to see how many sunspots there are. Nevertheless, a link seems to exist, according to the 5 nesting groups that were looked at. This isn't something that affects just blue tits, or even species like homing pigeons that are sensitive to magnetic fluctuations, who fly different routes depending on what time in the 11-year cycle it is. I'm talking about the last unmentioned point in my horoscope, bad health. There are numerous studies on how solar cycles might influence us. In 2011, a study spanning 2 decades of nearly 1/3 of women in Holland discovered a peak in 6 cervical pathologies that took place just after solar maximum, when the sun's radiation was hitting hardest. The study also checked 1 man during the same period, which admittedly is a much smaller number of candidates. Still, it was interesting to note that the man experienced slight elevations in oral temperature, pulse rate, blood pressure, and respiration rate that took place soon after solar maximum too. It's not just physical. There's even an influence on the rate of mental disorders. A study in 2006 looked at 237,000 clients in the main Medicaid database collected between 1995 and 2004. They found that, of all those clients, those born during higher energy chaotic cycles experienced an increased rate in mental disorders. If this is the case, then the cycle of the sun at the moment of your birth might just have influenced the course of your life. It's not quite star signs, but astrology might just be onto something, at least with one specific star. Ultimately, the science on this is still ongoing, and it should be stressed that any health impacts caused by these cycles are extremely minor. As one researcher put it took hundreds of thousands of patients to even notice that there was a health impact. The sun cycle should not prevent you from living your life. We're currently heading towards a solar maximum, predicted to arrive in 2025. But for those who are worried, living through or being born in a solar maximum isn't all bad. The same study suggested that this radiation might lead to a rise in creativity and adaptability. Perhaps it was during one such cycle, 80,000 years ago, that a human brain was mutated to give it abstract thought and consciousness. If so, if they gave us the means to perceive the universe, we have much to thank solar maximums for. We wouldn't be us without them. By now you might have got a sense that while there is much we have learned about the sun, far more remains a surprising mystery. For the brightest object in our sky, the sun ironically keeps us in the dark about many of the hows and whys of its workings. But scientists are attempting right now to pierce the veil, and to do so, they are bringing to bear some impressive pieces of kit. Both NASA and ESA have sent spacecrafts to study the sun in the last decade. These missions are the closest we've ever been to our star, so close in fact that they are able to directly interact with its atmosphere. So why are we sending these spacecrafts to the sun? What will they do there? What have they found? and what makes each of these missions special and unique. Let's begin with NASA's contribution, the Parker Solar Probe. The Parker Solar Probe was announced in 2009 and launched on the 12th of August 2018 on a Delta IV Heavy rocket. It used 7 Venus flybys over nearly 7 years to gradually shrink its orbit around the Sun. Just in the last month, on the 24th of December 2024, it achieved its closest pass yet to the Sun, so close to the Sun's surface that the probe was only about 6.16 million kilometers away, which is inside the Sun's corona, or its atmosphere. Being that close would feel like 500 suns in the sky beating down at the same time, with the temperature reaching up to 1,400 degrees Celsius. The spacecraft is going 7 times closer to the Sun than any spacecraft has gone before, and at these temperatures, many components that are used to make sensitive equipment for spacecraft would melt away. To protect the spacecraft and all its equipment, it is shielded by an 11 centimeter thick carbon composite shield, which can withstand these high temperatures. This shield also has a white reflective surface that can help minimize heat absorption. The shield will always be facing the Sun, protecting the spacecraft in this harsh environment. Being far away from Earth and orbiting a very dangerous object, this spacecraft is, by necessity, as autonomous as a space mission has ever been. Because the heat shield always has to be facing the Sun, for large sections of its orbit, it won't be able to point its antenna at Earth. During these times of communication blackout, it will control each of the sensors, control the formatting of data products, and archive high-resolution data until it can communicate with Earth again and transmit back what it has captured. ESA's Solar Orbiter mission began development in 2012, and after 8 years, the Solar Orbiter was launched on February 10th, 2020 on an Atlas V rocket. The Solar Orbiter also used gravity assist from Venus as well as Earth. These swing-bys put the Solar Orbiter into an initial 180-day orbit around the Sun. The spacecraft reaches its closest approach to the Sun every 6 months, at around 43 million kilometers away. This is comparatively much further away than the Parker probe's closest approaches, but just to give you an idea of the temperatures at this distance still, at 43 million kilometers from the Sun, the temperature can reach up to 500 degrees Celsius, as the sunlight will be 13 times more intense than what we feel on Earth. The Solar Orbiter is protected by a heat shield made with titanium foil layers about 40 centimeters thick, which is not as effective as the Parker probe's heat shield, but still enough to protect the spacecraft on its dangerous mission. The objectives of the Parker Solar Probe and the Solar Orbiter are similar to a great extent. Both these missions aim to find out more about our Sun's corona, its solar winds, coronal mass ejections, the structure of the Sun's magnetic field, and simply how it all fits together. The number of particles ejected by the Sun is not constant. Reconnection events in the Sun's magnetic field can release huge amounts of energy in the corona, ejecting millions of tons of charged particles into space in one big eruption. As mentioned before, this is what is known as a coronal mass ejection, or a CME. When these CMEs interact with the Earth's magnetosphere, it causes what's called a geomagnetic storm, and the biggest of these storms can be devastating. How devastating? To answer that, we'd need to look at the largest such event to ever impact the Earth, the Carrington event. From the 28th of August to the 2nd of September 1859, many sunspots appeared on the Sun in one place. On the 29th of August, southern auroras were observed as far north as Queensland, Australia, which implies a solar storm was occurring. Before midday on the 1st of September, amateur astronomers Richard Carrington, who the event was named after, and Richard Hodgson separately saw and recorded an extremely bright solar flare. Carrington and Hodgson wrote reports independently, which were both later published in scientific journals. The flare was connected to a major coronal mass ejection that traveled directly towards the Earth, taking 17.6 hours to make the 150 million kilometer journey, much faster than the speed of normal CMEs. Typically, CMEs take several days to reach Earth. It is thought that the high speed of the CME was made possible by a prior CME, perhaps the cause of the large aurora event on the 29th of August that cleared any ambient solar wind plasma for the Carrington event, like a giant slipstream. With the slipstream in place, the way was set for the biggest CME known to man. On the 1st to the 2nd of September 1859, the largest recorded geomagnetic storm occurred. Auroras were seen around the world, all across the northern hemisphere to as far south as the Caribbean. The auroras over the Rocky Mountains in the US were so bright that the green glow woke local gold miners, who began making breakfast as they believed it was morning. It was reported that because the aurora was so bright, people in the northeastern United States could still read a newspaper. The aurora was visible as far from the poles as sub-Saharan Africa, Monterey and Tampico in Mexico, Queensland, Cuba, Hawaii, and even at lower latitudes very close to the equator, such as Colombia. This is unprecedented, as typically auroras aren't visible at middle latitudes. By the 3rd of September, the aurora in the sky was said to be the brightest and most brilliant it had ever been. However, although beautiful, this storm also brought unforeseen problems. A consequence of the geomagnetic storm was that the electrically charged particles from the sun surged telegraph systems all over Europe and North America, which caused them to fail, even in some cases giving the people that operated the telegraph equipment electric shocks. Telegraph pylons threw sparks from the charged atmosphere. Amazingly, some telegraph operators could still continue to send and receive messages even though they had disconnected their power supplies. The storm was comparable to a hemisphere-wide EMP bomb, fairly harmless to humans, but extremely bad for electronics. The force of the CME in 1859 was so strong that it compressed the magnetic field of Earth all the way down to its atmosphere. Due to the fact that North America and Europe were facing the sun at the time, these areas of the world were most affected from the initial cannonball of the CME. Looking back at geomagnetic storms since the 1850s, there have been a few which were big but not devastating. For example, in March 1989, a CME hit Earth, rendering satellites unusable for several hours and jamming radio stations in Europe. Power in Quebec was knocked out for about a day. Some people there incorrectly thought the Soviets were attacking, and the glow in the sky was the result of nuclear bombs. Thankfully though, this solar storm and many like it did no real permanent damage. Today, if a CME the size of the Carrington event or bigger was to hit Earth, the consequences would be far more disastrous than they were for mankind in the 1800s. Technology was only just picking up back then, whereas today we have satellites in space, computers, telecommunications, power plants and more that would all be severely damaged in such an event. Due to the range of a solar storm, it would greatly impact equipment over a large area, the most susceptible technologies being the electricity grid and telecommunications, which have cables stretched out over a large distance. Without proper safeguards in place, transformers on the power grid could break, and millions upon millions would be without power for lengthy periods of time. If transformers did get damaged, for example, it would take years to replace, as transformers take years to manufacture. Often, these transformers are tailor-made for a specific requirement and are not mass-produced. Without power, refrigerators would not be able to stop food from spoiling, and as the transport system would also be down, as fuel stations require electricity to pump, replacing that food would be problematic. Payment systems that rely on credit cards would not work. People would not have access to the internet, as computers would not have power and battery-powered devices would run out of power quickly. Radio and TV stations would be disrupted. Hospitals would struggle when the backup generators ran out of fuel. we would be completely cut off from the outside world. The world is simply so dependent on technology, and especially on electricity, it is feared we have lost the ability to function as a society without it. Just look at the reaction when TikTok went offline for less than 24 hours in America recently. And worryingly, it is our power grid that is most vulnerable to a super solar storm. An independent think tank recently put the cost of damages to the USA alone at $2.6 trillion, ultimately destroying the economy. Unfortunately, that does not cover the social impact it could have. As is often the case in natural disasters, some people will undoubtedly resort to more primitive instincts, with attitudes such as every man for himself. Chaos, looting, and disregard for the law could occur. This would only get worse the longer the population goes without hearing from their government or organization of authority. Hopefully, in such a situation, the good of mankind would prevail, but it is a possible scenario. The think tank placed the estimated recovery time to repair the damage of the CME at 4 to 10 years, and estimated that 2/3 of the US population could die of starvation, disease, and chaos during this time. This might sound a little bleak, but when it comes to the sun, it's better to know the dangers than hope they aren't there. Unfortunately, CMEs are fast. They've been shown to reach Earth in just 17 hours. This might not be enough time to alert the entire population, turn off reactors, and take necessary precautions. In reality, we have simply been lucky up until this point, as we missed a Carrington-sized event hitting us by a margin of 9 days in July 2012. Had it been 9 days later, Earth would have been a bit further in its orbit and in the CME's path. This is why it's so important for us as a delicate species to understand the sun's corona so we can better predict solar storms, to give us better warning and hopefully avoid damages associated with a Carrington-sized event actually hitting us. It's just a matter of when rather than if. Now, these two probes may seem similar, and while a lot of their goals do overlap, they both have some unique features. The Parker probe is going deep into the sun's corona, where no man-made object has gone before. Because it has to withstand such high temperatures, the spacecraft is limited in some ways. For example, it cannot take pictures of the sun, as no current camera technology could look directly at the sun from that close and survive. But the Parker probe has instruments that can directly sample and collect data about the particles that exist in the sun's corona, and even closely study the regions where solar winds originate, something that can't be done at a distance. The Parker probe is lighter, smaller, and has less equipment compared to the solar orbiter. The solar orbiter, on the other hand, carries both particle detectors and telescopes. It can take close-up pictures of fascinating solar landscapes, and due to its orbit, it is able to track a region of the solar atmosphere for much longer than is possible from Earth. This enables it to observe storms building up in the atmosphere over several days. So, as you can see, these probes are complementary, and both will help further our understanding of the sun's corona in their own way. So, what have these missions achieved so far? Well, as mentioned, on the 24th of December 2024, the Parker probe passed within 6.16 million kilometers of our star, the closest any spacecraft has ever been. It also became the fastest traveling man-made object ever, traveling at 692,000 kilometers per hour on its daredevil dive. The data sent back from the Parker probe is already helping our understanding of how the sun's magnetic field and the corona interact to form solar winds. The probe also discovered that some magnetic fields from the sun sweep through the solar atmosphere, which can increase the solar wind speeds by as much as 500,000 kilometers per hour. In addition, it has discovered evidence of a dust-free zone 5.6 million kilometers from the sun. It's believed this is due to the vaporization of cosmic dust particles by the sun's radiation. The solar orbiter has already sent back its first images of the sun, and scientists found something called campfires, which you can see here. These are explosions on the Sun's surface that occur as a result of disturbances in small magnetic fields. The solar orbiter also took the closest images in existence of the Sun's surface from 77 million kilometers away, and the examination of particles across its orbit will help us understand the different types of space weather. But perhaps one of the most incredible discoveries from these probes was not what they saw from our Sun, but what they heard. Which begs the question, what does the Sun sound like? It's a simple enough question, and one that comes with a simple enough answer. The Sun is silent, of course. Because sound doesn't travel in a vacuum, to us, the Sun sounds like nothing at all. But let's do away with simple answers. What if sound actually could propagate through space? Without a giant cosmic muffler between us and our closest star, what would we hear? Would the Sun sing to us, an enchanting melody in our sky, or would its noise be such a cataclysmic cacophony, it would instantly be the last thing we ever heard? Scientists actually have the answer. Through spacecraft like the Parker probe, which is currently making skimming orbits around the Sun, they can detect the kind of pressure waves and particles emitted by the Sun and can convert those waves into the sounds we might hear if space was capable of such propagation. And interestingly enough, not all of the Sun's sounds are the same. And these sounds may allow scientists to solve two of the Sun's greatest mysteries. In our imaginary scenario, where space has suddenly gained the ability to propagate sound, we can now start listening to the Sun all away from Earth. Although the Earth is 152 million kilometers away from the Sun on average, it's perhaps unsurprising to learn that the Sun is very loud, easily audible from where we are. It would sound something like this. Just a reminder, there is no sound in space. This is a sound reconstruction, turning amplitudes and frequencies into sound waves, creating clips of what the waves might sound like to the human ear if an atmosphere were present. This soothing buzz has an almost electrical feel to it. It reminds me of generators, or perhaps even something vaguely radioactive, which is appropriate given that this is the Sun we're talking about. The nuclear fusion going on inside the Sun is equal to 3.85 times 10 to the power 26 watts every second. About 1,000,000 times more than what humanity produces in an entire year. All of this power being created has an unsurprising knock-on effect on the volume of the sound the Sun would produce. To get a sense of what this would be like, take the device that you're watching this on and connect it up to the speakers that they use at your next rock concert. Then play this noise at full blast. At 110 decibels, this volume level is survivable for short periods of time, but would likely end up with the entire population of the planet going deaf if they weren't wearing earplugs as it plays in our sky non-stop. In fact, we can consider it extremely fortunate that we don't actually have to deal with this. Species would have probably evolved with no ears, as hearing would be pointless. If we get closer to the surface of the Sun, that sound level grows exponentially, with some experts rating it at 270 decibels. Remember, decibels are a logarithmic scale, so every 10 decibels higher it goes, you have to multiply the sound level by 10. To get a sense of how loud this would be, 270 decibels is louder than our atmosphere itself can physically convey. There is a cap on sound at 190 decibels in Earth's atmosphere, as different mediums have different volume caps, due to some complicated quirks of wave amplitude and energy levels, which we won't go into here. The volume of the Sun would be 100 million times higher than this cap. The Sun is loud. Which is a shame, as some of the Sun's sounds can only be differentiated when we enter that ear-splitting zone. By the time the noise of the Sun has reached us, many of the Sun's sounds have blurred into one, meaning we miss out on some of their fascinating intricacies. To gain a better insight into the Sun, we would need to get closer, entering into that blisteringly loud zone of noise. So let's ignore the volume of the sun for now, and instead let's focus on its sound patterns. If we were to enter a spacecraft and head towards the sun, we would soon begin to hear a difference in the sound's uniformity. Rather than a constant buzzing, we would hear something like this. This is the sound of the solar wind. The sun emits a constant stream of charged particles that blasts out across the solar system, and its existence represents one of the sun's greatest enigmas to date. You see, it's tempting to think of this stream from starting inside the sun and blasting outward under the incredible force of all that nuclear fusion. However, by the 1960s, an important discovery had been made through observation. Although particles within the sun's atmosphere, or corona, were moving around with an average speed of 145 meters per second, particles outside of the corona were traveling at 618 meters per second. This meant that particles that had enough speed to escape from the sun's surface were drifting into space, and then something in the sun's corona was hyper-accelerating them from subsonic to supersonic speeds, firing them off. What kind of process or mechanism is doing this remains a mystery to this day. The corona contains a second enigma too. It is far too hot. Although you might expect the center of the sun to be the warmest part of it, and the temperature to gradually go down the further from the center you go, this stops being true once you enter the corona. The surface of the sun has an average temperature of 5,500 degrees Celsius, but within a few kilometers, the corona suddenly sees the temperature jump to as high as 2 million degrees Celsius. Something in the sun's corona is flicking solar wind into space, and something is making things very hot. Scientists do not know why this is happening either, although it is thought to have something to do with magnetic fields. It's here that we would meet the third sound of our tour of the sun. As our spaceship would draw closer and we passed over the boundary between the corona and empty space, something known in science as the Alphen surface, we would begin to hear the following. These are known as Langmuir waves. They are formed by tiny oscillations of plasma particles vibrated by light itself as they stream from the sun through tiny funnels on the sun's surface, a magnetic equivalent to the sound a kettle makes when it boils. We have entered one such stream. Countless of these streams fire out from the sun's surface. The sun's exterior is covered in islands of hot material rising from the star's center, the granules we mentioned earlier. Once there, the material cools and sinks back into the star's mass along the granules' edges. And something about this process of rising and falling material, or something going on within the sun itself, makes these sinking zones stream out powerful magnetic field lines. Plasma is scooped up by the magnetic force and is sent streaming into space, the starting point of the solar wind. Scientists don't know what causes this process, but the sound of Langmuir waves is eerily beautiful. As the winds head out, not all the waves created in this way travel at the same speed. This has the effect of spreading out sounds, as faster parts of the wave run ahead while slower parts of the wave fall behind, creating what are known as dispersive waves. Such waves are filled with chirps, little eddies of sound where fast waves coming from behind meet slow waves already traveling ahead. Eventually, this evens out into the hum we heard at the beginning. There is one last sound that might offer an insight into the entire mystery, one that has some intriguing implications. Here, right within the sun's boiling corona, we can finally begin to detect Whistler mode waves. Whistler waves are the distant echo of high-energy events that ring through the plasma of a celestial body's magnetosphere. We get them on Earth. Whenever lightning cracks, you get more than just thunder. a ripple travels through the planet's magnetosphere that can be picked up kilometers away if you have the right detectors. To truly get a sense of the scale of these waves, here is what they sound like on Earth. Just a few small little cracks and whistles, nothing too special. Now, here's what they sound like on the Sun. To go from sparse, brief clicks to a cacophony of wailing wind indicates that the Sun's magnetosphere is not just experiencing the odd crack of lightning. Something is going on constantly, all over, merging individual moments together into one incessant roar. Scientists are still trying to figure out what that roar is being caused by, but at least one theory for the force behind this sound, which can account for the dramatic acceleration and superheating of matter within the corona, is a dry-sounding little event called magnetic reconnection. Magnetic reconnection sounds fairly innocuous, and yet its innocent, technical-sounding name disguises a cataclysm. The Sun is a tensely wound-up ball of shifting magnetic field lines, all due to that churning plasma within its heart. I cannot stress enough how powerful these are. When magnetic field lines travel away from the Sun, it's sometimes possible for them to merge with other field lines, causing some of those iconic loops to form that you've likely seen in images of the Sun before. However, at the moment such arcs are formed, all hell breaks loose. When two parallel lines touch, creating an arc, there's a massive realignment in the excess field line's polarity. Everything above the arc needs to find a place to go to ensure magnetic equilibrium is maintained. Cut from their tethers, the field lines further out from the Sun form an arc of their own, which then catapults off into space like the releasing of a gargantuan stretched rubber band. This rapidly accelerating magnetic force is known as a nanoflare, and it indirectly heats the corona above it to multi-millions of degrees in seconds. Scientists have only recently developed the capability to be able to even see nanoflares, and aren't entirely certain the nanoflares they've seen are indeed the hypothesized events they were expecting, although they do seem to be accompanied by the expected superheating. This is an explanation that is still being worked out. Most of it is not yet understood. And still, it's not completely far-fetched that such moments when the Sun gets so wound up it snaps explain why its corona is as hot as it is, and why it is flinging solar winds out across the solar system with quite the force we witness. Although, to go from a single crack into the roaring wail that we hear, and to account for the constant solar wind travelling outwards in all directions from the Sun, nanoflares, or whatever the force behind this phenomenon is, must be extremely widespread throughout the entire corona. The Sun continues to hold many mysteries. The Parker Solar Probe, which collected many of these sounds, continues its journey around the Sun, gathering valuable data with every pass. The Parker Probe is nearly at the end of its 7-year mission, but hopefully it will collect plenty more information for scientists to pore over. Perhaps they will find more sounds for us, each one a clue to the ancient riddle of how the universe works. Because ironically, just like listening to the ticking of a clock to try and figure out how the clockwork functions, the secrets to the Sun might one day be solved by what we hear rather than by what we see. You might think that if we are able to get probes like the Parker Probe into orbit around our Sun, then it should be easy enough to get other things to our Sun too. Have you ever wondered if the Sun might be a solution to some of Earth's disposal problems? There are plastics and landfill items, the types of things you might throw out at home, and then there's dangerous industrial waste like nuclear byproducts, biohazards, and chemical toxins. These stifle ecosystems and affect the health of vulnerable communities the world over. So far, the best solution we could come up with for disposing of nuclear waste is burying it deep underground. not ideal when you consider that the stuff remains dangerously radioactive for tens of thousands of years. So why don't we just strap it to a rocket and blast it into the sun, like launching a missile at a target? Wouldn't that solve all our problems? This was a question posed to us by members of our community on Patreon, and its answer is not as straightforward as you might think. To begin answering our question, it's actually really hard to crash anything into the sun. Let's take a closer look. Suppose we've gathered together a massive pile of toxic waste destined for the sun. The first thing we'd need to figure out is how to get it into space. Easy, right? We've been launching stuff into space for the better half of a century. To get our trash pack through the atmosphere and out past Earth's orbit, we need to accelerate it to a velocity of 11.2 kilometers per second. This is the speed known as the escape velocity, where the kinetic energy of the payload surpasses Earth's gravitational potential energy. Once free of Earth's orbit, our garbage craft is on course for solar collision, right? Wrong. Once our package escapes Earth's orbit, it's still gravitationally bound to the sun. Put super simply, Earth and everything on it is moving sideways relative to the sun at 30 kilometers per second. Combining this sideways motion with the gravitational pull of the sun is what keeps us locked in an orbit. If the sun were to somehow lose its gravitational pull, we'd fly right past it at 30 kilometers per second and keep going. If we on Earth were to lose our sideways motion, we'd only be influenced by sun's gravity and fall straight into it. So there's hope for our garbage ball yet. How could we lose our sideways motion to make this solar freefall happen? Well, there's two options. The first option is to bring up enough fuel to brake in space. Now, technically speaking, you can't really brake in the vacuum of space, but the next best thing would be to configure our garbage payload's propulsion system to generate thrust opposite to its direction of sideways motion. This cancels out the sideways motion, slowing the spacecraft down and letting the sun's gravity do its thing. Earth orbits the sun at 30 kilometers per second. So to brake a garbage rocket launched from Earth, you'd need to be able to accelerate 30 kilometers per second in the opposite direction of its movement. Here's where it gets weird. The closer you are to the sun, the harder it is to crash into it. Let me explain. The closer you are to the sun, the faster your orbital velocity. Mercury orbits at a dizzying 48 kilometers per second, while Pluto cruises at a cool 4.7 kilometers per second. The faster your orbital velocity, the more you'll need to decelerate to free fall into the sun. That's why it is actually much more fuel efficient to fly to the outer solar system, decelerate, and free fall into the sun from there. It's not inconceivable to accelerate a spacecraft 30 kilometers per second. As mentioned, NASA's Parker Solar Probe accelerated well beyond that, making it the fastest man-made spacecraft ever. But this brings us back to the problem of fuel. To make this brake and fall method work, you'd first have to launch your garbage payload into orbit with Earth, then launch the fuel for the journey into orbit. Once both pieces are orbiting Earth, you can fuel up your payload and accelerate it past Earth's orbit into orbit around the Sun. Then you'd have to use the remaining fuel to decelerate so that it free falls into the Sun. Why not launch both the payload and fuel at the same time, I hear you ask? Well, the problem is, it's simply too much fuel. For context, the Saturn V rocket that took man to the moon needed 2 million liters of fuel just to leave Earth's orbit at 11.2 kilometers per second. A mission like this would require orders of magnitude more fuel. No modern rocket technology would even come close to being able to carry the amount needed for a journey like this. Okay, so scenario 1 is out. What other options have we got? Another way to decelerate in space is with a gravity assist. Usually when we talk about gravity assists, we are thinking of the kind that slingshot the Voyager probes into the outer solar system. However, gravity assists aren't only used to speed probes up. they can also slow them down. If you were to approach a planet from behind, fly in front of it, and exit behind the planet like this, your spacecraft loses energy while the planet gains energy. The Messenger and Bepi-Colombo probes have both successfully used this gravitational assist technique to lose velocity and enter orbit around Mercury. The thing is, this takes a lot of time. Bepi-Colombo was launched in 2018 and will only arrive into orbit around Mercury in 2025. Surprisingly, its path to get there is longer than the distance between Earth and Pluto. This is because, to slow down enough, one gravitational assist won't do. In fact, Bepi-Colombo needs 9 different gravity assists to slow down enough to orbit Mercury. Similarly, crashing our garbage into the Sun is all a game of carefully calculated orbital mechanics. If we don't slow down enough, we'll be stuck in the Sun's orbit. If we slow down too abruptly, we might get caught in another orbit we don't want to be in. Okay, you might be thinking, but Alex, this is all feasible. It's hard, but it's within the realm of possibility. So why don't we just do it? Possible? Yes. Worth the time, effort, risk, and technical challenges? Probably not. Not to be a cynic, but think about what could go wrong. First of all, we're proposing packing a bunch of nuclear waste, biohazards, and plastic onto a rocket and launching it from Earth. A launch failure or explosion could be disastrous, to say the least. Even the world's most successful rocket, the Soyuz, has a 2 to 3% failure rate. I don't know about you, but when nuclear waste is at play, I don't like those odds. Even if the launch goes well, the project itself would be ridiculously expensive. So much so that no sane person would approve the budget. There are far too many other missions on the table that would bring so much more to science and humanity than a garbage disposal mission. And lastly, it would actually be easier, quicker, and cheaper, but still crazy expensive, to shoot our garbage out of the solar system toward interstellar space. It would be less fuel intensive since the acceleration required to escape the Sun's gravitational pull is 42.1 kilometers per second, just a 12.1 kilometers per second acceleration from Earth's orbital speed. So there you have it. We don't shoot garbage into the Sun because it's super hard, super risky, and super expensive. We're probably better off being more conscious about what we consume and how we recycle it. Let's return to that quiet hill where we began, watching the colors of sunrise. The Sun is an awe-inspiring part of our solar system, a crucial part of life here on Earth. I hope the next sunrise you see becomes that little bit more special. I hope the pink and orange photons, scattered for one final time on the molecules of Earth's atmosphere before streaming through your pupils, will make you think of the incredible voyage they have endured, beginning with the collapse of a colossal cosmic cloud into an element-building furnace, struggling for hundreds of thousands of years through a melting pot of plasma to gift you with this beautiful scene. I hope this exploration has deepened your appreciation for that daily miracle we often take for granted. And there's still so much more to uncover about our closest star, from the formations it will undergo to the profound impacts it will have on our solar system's future. Thank you for joining me on this journey through space and time. If you found this journey as enlightening as our host star, please give the video a like and fuse it with your own thoughts down in the comments below. Thanks for watching. Thanks for watching. And thanks to our crew of Astromnauts over at Patreon who help us make science knowledge freely available to everyone. Chasing the algorithm can be hit and miss sometimes, so your contributions help us keep making the content we love. And if you want to join the Patreon, there's never been a better time to get in on the party. Just sign up with the link in the description. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.